need to add basic logging to your FastMCP server without drowning in complex middleware configurations. We'll implement a simple logging middleware that tracks every operation from start to finish, showing you exactly how to intercept requests, log their progress, and handle errors, all in under 15 lines of code. From FastMCP server middleware, import middleware, middleware context. Class simple logging middleware, middleware. Async def on message, self context, middleware context, call next. Print F processing, context method from context source. Try. Result equals await call next, context. Print F completed context method. Return result. Accept exception as E. Print F failed context method, E. Raise. This demonstrates the interceptor pattern through FastMCP's middleware pipeline, a specialized form of the chain of responsibility pattern tailored for RPC systems. Middleware acts as modular interceptors that wrap core server logic, allowing you to inject cross-cutting concerns like logging, authentication, or rate limiting without modifying the underlying handlers. What makes this distinctive is its operation-aware design. Hooks target specific MCP operations, tool calls, resource reads, rather than generic HTTP routes, aligning with the protocol's semantic structure. The pattern works by creating a bidirectional processing chain where each middleware can inspect, modify, or short-circuit requests and responses. Pre-processing hooks execute before the core handler, enabling validation or transformation, while post-processing hooks run afterward for logging results or modifying outputs. The call next abstraction maintains the chain flow, and the hierarchical hook system, from generic on-message to specific on-call tool, lets you target interventions at the right level of granularity. This design preserves separation of concerns while enabling deep integration with the RPC lifecycle. This approach solves the boilerplate problem in RPC servers, where cross-cutting logic, like auth checks or metrics, would otherwise clutter every handler. By centralizing such logic in middleware, you keep tools and resources focused on business logic while maintaining consistency across all operations. The trade-off is added complexity in debugging, since control flows through multiple layers. But the benefit is composable, reusable infrastructure that scales with your server's needs. Use this when you need to enforce policies, collect metrics, or transform data uniformly across many endpoints. Let's break it down line by line. From FastMCP server middleware, import middleware, middleware context. Imports the base, middleware, class, and middleware context type from FastMCP's server middleware system. These provide the interface and request context needed to intercept and process messages in the FastMCP pipeline. Class simple logging middleware. This defines a middleware class that hooks into FastMCP's message processing pipeline. Middleware pattern lets you intercept, log, or modify messages before and after they're handled without changing core server logic. Inheriting from middleware ensures proper integration with the server's async processing chain. Async def on message, self context, middleware context, call next. This defines the middleware's core message handler, implementing FastMCP's middleware interface. The onMessage method intercepts every incoming message, while callNext delegates to the next middleware or final handler, classic middleware chain pattern. Async await enables non-blocking processing of concurrent requests. Print F processing, context method from context source. This logs the incoming message details before processing begins. The middleware pattern requires visibility into request flow, and this establishes the starting point for debugging and monitoring. This establishes an exception handling block, ensuring the middleware gracefully handles both successful and failed message processing. The try-catch pattern here prevents unhandled exceptions from crashing the message pipeline while still allowing errors to propagate up after logging. Result equals await call next, context. This invokes the next middleware in the chain, passing the context forward. The await ensures proper async execution flow while preserving the request-response cycle for logging completion or failure. This is the standard middleware delegation pattern in FastMCP. Print F completed context method. This logs successful message completion, providing visibility into the middleware pipeline's execution flow. It confirms the message was processed without errors, which is critical for debugging and monitoring in distributed systems. The pattern mirrors the initial processing log, creating a clear audit trail for each message lifecycle. Return result. This returns the processed result from call next to the middleware chain. Without this, the response would terminate here, breaking the pipeline. It's the explicit continuation pattern that maintains the async call flow. Accept exception as E. This catches all exceptions during message processing, ensuring the middleware doesn't silently swallow errors. The exception is re-raised after logging, maintaining the error chain while providing visibility into failures. Print F failed context method, E. This logs failed operations with specific error details. Critical for debugging, it captures both the failed method name and the exact exception, ensuring you know exactly what went wrong and where. Follows the standard error logging pattern before re-raising to maintain the exception chain. Raise. This re-raises the caught exception, preserving the original error stack trace. Critical for middleware transparency, it ensures failures propagate correctly to the caller rather than being silently swallowed. Middleware interception pattern. The on-message hook in FastMCP middleware creates an interception layer that wraps every request, executing both before and after the core operation through call next. Exception handling in middleware must explicitly re-raise caught exceptions to maintain the error chain. This pattern enables cross-cutting concerns without modifying individual tool implementations.
The middleware that sees everything becomes invisible to everything.